So my name is David, I'm the coordinator of the Maths Learning Centre, and I've come to talk to you about some assumed knowledge that might come up in an engineering or an economics course or any other course. There are plenty of other courses that have the same ones, but engineering and economics particularly. One of the main purposes today is to tell you what things are called here in Adelaide. So you may have seen them before, but you might know them under different names. And that's the most useful thing I can give you today. If you want to know more about some of these mathematical concepts, then you can come and visit the Maths Learning Centre when we're open and talk to one of the staff there. It might be me, and we can talk to you about it more. And there are some resources on the website to learn more about these things. So I'm going to write on the piece of paper here and talk about some things that your lecturers in general will expect you to know. That's a U, not a V. Functions. Okay. So in maths, a function is a rule which takes an input and produces an output. You will have seen it looking like this. So e.g. is how lecturers here write for example. I don't know why it's e.g., but that's what it is. It sounds like example. You'd expect it to be ex, but it's not. So e.g. is how we write example, and f, it will look like this in a maths textbook. Something like that. There will be some formula from which you take an x or a y or a t or some other letter, and there's some calculation to perform to produce the answer. So that's called a function, and this is called function notation. I'm really hoping you've seen this, or in your engineering classes your lecturers will be most surprised. So the idea is that you take that if you pick a particular number for x like 4, then you replace all the x's with 4 and figure out what the answer is. So what's that? 16 plus 1 minus 28, which would be minus 11. So f of, this is read aloud as f of 4 is minus 11, or is equal to. So this is read aloud as f of 4. It's not f times 4, it's f of 4. Okay, so that's great, but there are two things that you need to know about any particular kind of function, and you need to know how to do algebra. So what sorts of rules are there for rearranging formulas or for solving equations? And we also need to know what the graph looks like. Now I pronounce it as graph because I'm from New South Wales. Most of the South Australian lecturers will pronounce it as graph. So there you go. So you need to know how to do the algebra and how to draw the graph. And your lecturers don't really care all that much about you figuring out precisely what the graph looks like. They just want you to know the shape that it ought to have. So for example, this formula, what we do is we create an x and a y axis, and every point on that plane here has some coordinates. So maybe this point here would have the coordinates like 2, 2, because it lines up with 2 here on the x-axis and 2 here on the y-axis. This point here would be 1, 2, because it lines up with 1 on the x-axis, 2 on the y-axis. And every point I can tell if it's part of the graph if when I sub it into the formula, it works. So I know that if I put in 4, it's supposed to come out to minus 11. And so that point is on the graph, because f of 4 is minus 11. And you can draw all the dots and see what you get to create a graph. And if you join them all up, it will create a curve, and that will be your graph. This curve Well, I have no idea what this curve looks like. I presume it's something like that, but I don't actually know off the top of my head. So that's the idea of functions and their graphs. So what I'm going to do is a little whirlwind tour of the different kinds of functions and what their graphs ought to look like, and every so often a little bit of algebra that might go with them. So, linear functions. So linear functions are called linear because they describe straight lines, and they will usually look like something like that, where the x represents an x that you can put different numbers into, and the a and b are whatever numbers you're thinking of at the moment. So it might be f of x is a third of x minus 7, something like that. So this number here is called the slope, though some people will call it the gradient. And this number here is called the, what was that? Constant, yes. And it's also called the y-intercept. The reason it's called the y-intercept is that that number is where the line will cross the y-axis. And this slope is representing a rise over run, they call it. The 1 is how far up it goes, and the 3 is how far across it goes. So that means that for every 3 across, so it starts here at minus 7, for every 3 across, it goes up 1. And so that means that it's something like that. And that's how the shape of that graph is related to its formula. And that's the biggest idea in most of mathematics, is that the formula for a graph will tell you about the shape of an object that you can draw. I should point out that some linear formulas, equations as opposed to functions, need to be rearranged in order to get a function. So it's possible that you might see something that looks like this. And that is also a linear equation. And it also represents a straight line. You can rearrange that equation to create the other version. If I divide everything by 5, note that was a bad plan, just a second. So we would like it to be y equals, so we'll move the 5x first, which means we'll subtract 5x from both sides. And then we'll divide by this minus 7. And now it's in the slope-intercept form. It's not actually necessary to rearrange it to draw the graph, though. So especially in economics, you don't need to redraw the graph to rearrange it to draw the graph. You can instead do this and say, well, if I can figure out where it meets the x-axis and the y-axis, I can draw my graph. If x is 0, I get 7y is 35, so y must be minus 5, so it crosses at y equals minus 5. If y is 0, I'll cover that up. 5x is 35, so x must be 7. So it crosses the x-axis at 7, and I can join those points up. It's supposed to go through there. And that will make my straight line. It's a useful trick. What's that? Oh, can I repeat that? So Yes? So I'll write some working out on the page to show what I did as well. So if x is equal to 0, then I get 5 times 0 minus 7y equals 35, which is just minus 7y equals 35. I can divide both sides by 7 to get minus 5. And that gives me this point here, because x is 0 and y is minus 5. If y is 0, I get 5x minus 7 times 0 equals 35, which means x would have to be 7, and that gives me this point here. It's a very useful way to draw a graph. In economics, they tend to not occur down here, they're usually up here. So. Okay. The next kind of graph is a kind of function or graph is a quadratic. A quadratic function, which will normally look like, its formula will look something like this. Or it might not be a y, it might be an f of x. And its shape will look something like this. One of those two. It depends on what this number is here. So if this number here, which is called the leading coefficient, so it's a coefficient because it's a number attached to one of the x's. It's leading because it's the one at the front. So the leading coefficient, if the leading coefficient is positive, then your graph will go upwards like that. If the leading coefficient is negative, it'll go downwards like that. And lots of lecturers will shorten positive to plus VE and negative to minus VE. So plusative, if you like. So that's just how they'll write it on the page instead of writing the whole word positive. So this, if you look at it like this, the fact that it's got a squared tells you that it's one of these two shapes. Whether this is a positive number or a negative number tells you which of the two shapes it is. And if you rewrite that, do some algebra, you can create your formula. You can find out more information from your formula. So if instead the formula is written this way, I'm just reusing all my letters. If your formula looks like that, a, x minus d, x minus e, for some numbers here, then these numbers here are called the x-intercepts of the graph, or they might be called the zeros. I think you don't have an e in zeros actually. The zeros. They won't be the number 0. They're called zeros because when you put them into the formula, the answer is 0. And your graph will look something like this. And this will be the point D, and this will be the point E on the x-axis there. Point here is that if you rewrite your formula in a different way, you can get different information about the graph. This shape, by the way, is called a parabola. Parabola. That's how it's pronounced here. It literally means like a ball. Because it's the shape a ball makes when you throw it. Okay, now doing well on our tour of functions. The next one is a cubic, it's called. Which will have, y equals something x cubed plus and so on. So there'll be other stuff here. There'll be x squared and x and a constant. It's called cubic because we've got x cubed here. This number here is called the degree. The degree is 3. It's a degree 3. And cubics have the tendency to look like this, or like this, or they may look like that, or like that. Okay, so cubics, the two ends point in opposite directions. It may be that it has a couple of turning points, it may be that it doesn't. That's not supposed to be a sharp kink. It's very useful to be able to draw shapes like this the moment you see the graph, because then you can say, well, I expect there to be turning points. So this is a turning point, it's called. It's also known as a stationary point. And that's stationary with an A. Stationary meaning staying still. And the reason it's called a stationary point is because if an object was moving along this curve, it would stop going up and start going down. So it would be still for a moment at the top of the curve. That's why it's called stationary. So stationary points. So a cubic can have two stationary points. It might have none, or it might have two. And then the next one is called a quartic. And it has its degree 4. So we had linear functions, quadratic functions, cubic functions, quartic functions, and quartics can have up to 3 turning points. Well, maybe not that sharp. And they can do even all sorts of interesting things. So quartics have a whole lot more different options. I haven't even drawn all of the options here. But one thing that they share is that the two ends point in the same direction, both down or both up. So all of these functions so far are called polynomials. That includes the linear, the quadratic, the cubic, the quartic, and anything above that. They're all called polynomials. So a polynomial could have any number here. Okay? As long as it's all made out of x's to the power of something, it's called a polynomial. And polynomials have very useful information that you can know about them. If the degree is odd, if the degree is an odd number, so a cubic is x cubed, or an x to the 5, or an x to the 7, then the two ends of the function will point in opposite directions. But if the degree is even, then the two ends will point in the same direction. So that's the most useful piece of information about a polynomial. If you want to know more, I can tell you, and I'm just going to write a note for myself. I do have a document which talks about polynomials in great detail. So, yeah, I won't put it there. I'm just going to put a note somewhere on the back of this to say to remind myself to put the polynomial notes on the website. Okay. So all of those graphs are polynomials. They are the, in inverted commas, simplest kind. Some of them are quite complicated, but they're the simplest kind of function because they're made out of powers of x all added together. There are a few more functions that it's very useful to know about and to know what they're called, so that if you want to know more, you can look them up on the internet. The next kind of function is called a rational function. So rational is the word that mathematicians use to talk about fractions. And so a rational function is created as a fraction of polynomials. So it will be something like some polynomial on the top and some polynomial on the bottom. Not the same one, because otherwise they'd cancel each other out. So I'm just going to give you a couple of examples. The classic and most important example is something like that. Okay, the top is technically a polynomial. That was the number 4. Just the plain number 4 is a polynomial. X is a polynomial too. So that is a rational function. That is the simplest kind of rational function, and it will look like this. So that's my x-axis. Sorry, that's my x-axis. That's my y-axis. The fact that the x is on the bottom means that I can't put x equals 0 into the formula because I'm not allowed to say 4 divided by 0. That doesn't mean anything. So that means that there's no value of the function here. And also, 4 divided by any number can't be 0. No matter how big the number is, I can't produce the answer 0. So this function never crosses the x-axis. So what it actually looks like is that it gets closer and closer to the x-axis as I go this way. It gets closer and closer to the y-axis as I go this way, and the same down here. The shape of this graph, if you want to know, is a hyperbola. But you don't need to necessarily know that, but it's worth noting in case you want to look it up. So that is the simplest kind. No matter what number I would have on the top, it would be roughly the same shape. It would just be more stretched out up this way. Okay, so if I had a 17, it would be, this bit would be a little bit further apart. So here is an example of a rational function. It's much more complex than the previous one. It's 4 plus x over x minus 1. And the easiest way to tell what the graph of this looks like is to make it look more like this function. So I'm going to show you some working out that will calculate what that looks like. So I'm going to rearrange this, because we know if we can write the function in the correct way, we will be able to figure out what the graph is supposed to look like. Just like with the quadratics, if I can factorize it, I can get the zeros. Well, I'm going to do that here too. So what I'm going to do is I'm going to make the numerator, the top here, look more like the bottom. So first I'll do this, because that makes it easier. And then I'll say, well, so before, I can't cover that up. Before I had x plus 4 over x take 1, and I'm going to subtract a 1 and add a 1, because I haven't really done anything then. And now, this divided by x take 1 is 1, and this divided by x take 1 is this. Why was that useful, you ask? Well, I can draw this because I know what y equals 5 over x looks like. 5 over x looks like that. And my function, instead of x, it has x take 1, which means it's moved in the opposite direction on the x-axis. Just give me a second. I'm going to put the -1 over here. So I've got this here. So it was like this. A -1 next to the x means that it doesn't happen here, it happens 1 in the positive. So instead of a -1, I move it +1. And a -1 next to the y means that instead of moving it -1, I move it +1. You always do the opposite. So I have the same graph, it's just here instead. If you want to know more about doing that, feel free to come and ask. It's a fun game, I think. It's one of my favourite things about functions. So it is one of the things that in economics is extremely useful to be able to say, well, at least I know if I ignore the -1 next to the x and ignore the -1 next to the y, at least I know it's the right shape. It's a hyperbola shape, and that's the most useful thing that you can know. All right. The next thing. Now I will scan these and put these notes on my website as well, so that you can find them. So what have we done? We've done polynomials. We've done rational functions. The next kind of graph is an exponential function. Exponential, yes, that's right. So an exponential function has a tendency to look something like, the formulas will be like this, something like that, 5 to the power of x. This is different to your polynomial because your polynomial would be more like x to the power of 5, but this one has the x in the power. Or it might be more complicated and be 2.7 times e to the power of x, something like that. This number e is something in your calculator. If you've never met it before, it's about 2.7 actually. But it's a very useful number and will occur a lot of times. And these tend to look like this. They go up very fast over this side and go down very slowly on this side. So just a note for the way people talk about these things. When I write 2 to the power of 3, this is sometimes called the power. Sometimes it's called an index. And the plural of index is indices. Or sometimes it's called the exponent, which is where the word exponential comes from. But you'll hear it, you might, depending on who your teachers are or where you're looking on the internet for resources, you might hear it called by any of those names. And some people read this aloud as 2 to the power of 3, or they'll just say 2 to the 3. So, you can do the same trick as you do with the other functions of moving things over. So if I had something like that, y equals 5 to the power of x plus 4 minus 7. Then if I rewrote it like this, well, I could imagine that without the plus 7 and without the plus 4, it would just be y equals 5 to the x. And y equals 5 to the x would normally look like this. as we drew it up there. We already drew y equals 5 to the x. That's what that looks like there. Our graph is the same shape, but it's not at, it doesn't happen here at 0, 0. Plus 7 means I move it back 7. And plus 4 means sorry, wrong way. Plus 7 with the y means I move it down 7. Plus 4 with the x means I move it back 4. And this is where I'm going to draw it instead. So my graph has moved over because of these things here. Really useful stuff to know. But the point, though, the most important point is that it is still the same shape as it was before. That shape is what you're looking for when you're trying to get instinct as to how a formula or a function is supposed to work. All right. And the last kind of function that I want to tell you about is the opposite of this. Is a logarithmic function. What was that? I can't even hear beyond the edge of this. This air conditioner is awful. Nope. There are no controls for the air conditioning. So a a logarithmic function is made using a logarithm, and it will often look like this. So the most famous is ln. You may hear it pronounced as ln or lon. If you say it that way, half of your teachers will be extremely annoyed. Here in South Australia, we learn it as ln. We just say the letters. Yeah. Ellen, you know, the talk show host on American television. So, lnx, some places will just call it log. They'll just call it log and they'll mean the same thing. A calculator means something different with log than it does for ln. So I just thought I would point that out. And it looks like this. It's the opposite to your exponential graph. So we take this exponential and we turn it this way. You can just see it through the paper there, see? So we actually flip the whole thing that way and it becomes a logarithmic curve. So just some notes. When you take the number 2 and you perform 5 to the power of, and you put 2 in that spot there, 5 to the power of 2, the answer you get is 25. The idea of a logarithm, is that if I want to go back from 25 to 2, I can do what they call log base 5. And I put a number in this spot here. So if I do 5 to the power of 2, the opposite of that is log base 5 of 25. So I'm just going to write that down in actual words. 5 to the power of 2 is 25, and log base 5 of 25 is 2. So that's the idea of a logarithm. It's designed to do the opposite of a power. And this number 5 here at the bottom is the same as this number 5 here at the bottom. Right. So I'm not going to draw any more graphs of logarithmic curves, but I am going to show you how to solve an equation using logs, because that's a useful skill. So we're going to have an example of an equation. 15 is 3 to the power of x. So my idea is I want to figure out a number x such that 3 to the power of x is 15. So 3 to the power of 2 would be 9, and 3 to the power of 3 would be 27. So I need something that's somewhere between 2 and 3. I can figure it out exactly by doing ln on both sides. This is the usual way of solving this. I could do log base 3, but my calculator doesn't know what log base 3 is, but it does know what ln is. The laws of logs say that if you have a power inside, it can come out the front as a multiplication. Like that. And then ln3 is just a number. I don't know what it is. It's about, I don't know, 1 point something. ln3 is a number. I can divide both sides of my equation by that number. So x times ln3 then divided by ln3 gives me x again. ln15 divided by ln3 is that. And that means that x is whatever this number works out to. Going to ask my computer that. So equals it's apparently 2.46497. So what was that? I'll do it to 3 decimal places, hey? 2.465. So you need a calculator or a computer to do that last step. But that's how you can solve an equation that involves a log. Okay. Well, that's everything that I could care to tell you about functions in 40 minutes. You've done quite well. The last thing that I would want to tell you is a little bit about calculus. So, calculus is an area of maths which is designed to find out information about functions. Okay, so it finds out information about functions such as where the turning points are. Calculus can help us when we know the formula for a function. We can figure out what these turning points are. We can figure out what these places here are called inflection points. We can, given a particular point anywhere, figure out the slope of the tangent line. This is a tangent. And we can also, using calculus, if we know where the x-axis and y-axis is, we can figure out an area as well. So calculus can allow us to find out all sorts of information about graphs. And the basic kind of calculus, well, I say basic not because it's easy, but because it's easier than all the other kinds, is differentiation. So, the derivative is the slope of the tangent at any particular point. So this line here is called a tangent. So if you pick a particular spot, you find the line that meets this curve in exactly one point. The derivative of the curve at that point is the slope of that tangent. And the notation for it is that if you've written your function as f of x like that, then normally you write the derivative as f like that. Some people call it f dash, some people call it f prime. If you've written your function as y equals, then you often write the derivative as dy over dx. They mean the same thing, okay? You are allowed to mix them together, but you often annoy the reader if you do that. But just to note that both of those represent the derivative. And the derivative is a new function, it's a new formula, but instead of calculating where the points on the curve are, it calculates the slope of the tangents. So, the process of finding the derivative is called differentiation. I do not. I left out a letter. Differentiation. Differentiation. Right, yes. Differentiation is the process of finding a derivative. And the opposite process of taking a derivative and finding what the original function is, the opposite process is called integration. In ordinary English, differentiation means being able to tell the difference between things, and integration means putting things together. Who knows? So it's because the tangent is almost about the difference between two successive points on the curve. So I can't go into all the details about about differentiation and all the philosophy of where it comes from, but what I can do is remind you of the basic rules of finding the formula for a derivative. So the rules for calculus for differentiation are: there is a power or exponent rule, which says that if you have y equals x to some power, this is a number as opposed to a letter, then the derivative, so I say it aloud usually, multiply by the current power and add -1 to the power. And this works for all powers of any kind. So, for example, x cubed will become multiplied by the current power, reduce the power by 1. X to the half will become multiplied by the current power, and we'll have a half minus 1, which gives me minus a half. And if it's already negative, x to the minus 2, I'll multiply by the current power and reduce the power by 1, and it will go even further down to -3. The power rule is extremely useful and works for every possible power. There's a rule which says that if y is just a constant, so maybe it's 5 or 7 or 208, dy on dx will be 0. So they're the most basic rules of differentiation, and they will get you a long way. The next rule, the addition rule. The addition rule says that if you have different pieces that are all added together or subtracted, you can do each piece separately. So each piece separately. So as an example, so that was the function I had to begin with on the first page. The derivative of y, I will multiply by the current power, and I'll reduce the power by 1, so the 2 will go down to a 1, but x to the 1 is the same as x. That's a constant, so it will become 0. I really should have said this as a separate rule, but this power is 1, so it will go down to minus. Can I add just before this? I don't even know what this rule is called, but if you see y equals some number times x, then dy on dx is just the number next to the x. So here I saw minus 7x, dy on dx is just minus 7. And they will take you a long way. So there are a couple more rules. If you have a constant multiple, so if you see y equals c times something, then dy on dx, if the c is multiplied on, it will stay there multiplied on, and you will differentiate whatever is next to it. It works better with an example. Y equals 15x cubed. Okay, so then dy on dx. The 15 is multiplied on, so it will still be multiplied on afterwards, and then I will multiply by the current power and reduce the power by 1. And so I will end up with 45x squared. Another example is that one. You don't have to expand it out the brackets. You can. I can do it if you want, but I can do it directly. The 2 is multiplied on, so it will still be there afterwards, and I can just differentiate the inside. So it's a very good rule, the constant multiple rule. I'm almost out of time, but I'm going to keep talking even if you have to leave and just record it, okay? So there's some special functions. If y is e to the power of x, then dy on dx is still e to the power of x. It doesn't change. If y is ln x, then dy on dx is 1 over x. And in case you're interested, if you have a number other than e in this spot here, so just as an example, 2 to the x, what you'll get is you still will have 2 to the x, but you will have to multiply by ln2. Just in case that comes up. Really, if that ever comes up and you can't remember, you can say, David knows about that. I'll visit the Maths Learning Centre and ask him. Okay, and then we have the last 3 rules that are the ones that you will hopefully have heard the names of. All the ones I've told you so far, most people don't give them a name. They're just rules. But these last 3, people have names for them. There is the product rule. And everyone here in Australia learns it as the product rule. And it's designed, instead of having a function where there's things added together, it's a function where there's things multiplied together. And it goes like this. If y is equal to some function multiplied by some other function, then when you do the derivative, you have 2 pieces actually. You differentiate one of them, but you keep the other, and then you keep one of them and differentiate the other. That's the product rule. So for example, y is x ln x. I have 2 things multiplied together, so I have to use the product rule. I can't use any of the other rules. If this was a constant number, I'd be fine, but it's an x. So I have to do this. So I will differentiate the x, which will give me a 1, because it's 1x. and I will keep the ln x. And then I will keep the x, but I will differentiate the ln x. And that leaves me with ln x plus 1. That's the product rule. The quotient rule is similar, but it's for fractions, because that's what quotient means. If y is equal to f of x divided by g of x. Now you may have seen these as a p and a q or a u and a v in the formulas that you're used to. Then dy on dx so I remember it in this order. It's similar to the product rule, but it's got a minus, and you always start with the derivative of the first one, the top one. So on the bottom though we have gx squared, and on the top we have the gx but it's not differentiated, and we have the fx but it is, and we also have the other combination, but we have to subtract them. This is the hardest one for most people to remember, and it's also the hardest one to get in the right order. You're not allowed to differentiate the bottom first, you have to keep it as it is. So the example would go something like that, a nice rational function. Right, I will keep the bottom and I will square it like that, and I will keep the bottom here, but I will multiply by the derivative of the top. So that differentiator gives me a 1. And on this side I'll keep the x plus 3, but I'll multiply by the 2, the derivative of the bottom, and the derivative of the bottom is 2. And usually at this stage you would expand this all out, so I get 2x plus 1 minus 2x plus 6. So the minus goes into both of those, and I get minus 5. Don't expand out the denominator, leave it with a square. That's the best plan. So some people would expand and we get 4x squared plus 4x plus 1. Don't do that, leave it as a square. That's perfectly acceptable and is less work. And there is one more rule, and it is called, here in South Australia, it's called the chain rule. When I learned it at school, my teacher didn't call it the chain rule. She called it the function of a function rule. You may also know it as the composition of functions rule. But here at school, when you learn it in South Australia, it's called the chain rule. And it goes like this. If you have this, then the derivative goes like this. Pretend that that's not a gx, but just an x, and differentiate it as if it was an x. And then put the gx back in and multiply by the derivative of the inside. So some people say differentiate the outside and then differentiate the inside. So you may also know it as this version. If y equals f of u and u equals g of x, so I've called this u, then dy on dx is dy on du times du on dx. You may see it that way as well. This is particularly common in physics, in engineering, this is much more common over in economics. And it makes so much more sense with an example. So here we go. I pretend that that's an x inside that function. So if that was just an x, I would have 7 to the power of 6, because that's what would have happened if it was an x. But it's not an x, it's actually a 3x squared plus 5x. So I have to multiply, you don't need the arrow in your working, it's just useful for me, by whatever the derivative of this is. So I have 3 lots of 2x and a 5. And so I now have 7, 6x plus 5, 3x squared plus 5x to the power of 6. Lovely. And this is one that will happen very often, like that. I have e to the 3x plus 1. So if it was just an x, I would have e to the x, and the derivative of e to the x is the same as it was before. But it's not an x, it's a 3x plus 1, so I have to multiply by the derivative of that, which is 3. And that's how the chain rule works. And then what will happen is that there are some situations where you will have to use the chain rule and the product rule at the same time. Or, yes, there will be many things that you might have to do. And so being good at those things is a good idea. There are some resources on the Maths Learning Centre's webpage to help remind you of some of those details and to give you some practice if you need it. Because, to be fair, many of the students who come from high school in South Australia and go straight into their degree, they've only had 3 months break and they've forgotten everything they've ever known. So it might have been a little longer for you, who knows? So it's okay to feel like you need to brush up on your skills. And if you're ever not sure on anything, even if you think you know what's going on but they've used different terminology here, visit the Maths Learning Centre and ask. It's our job at the Maths Learning Centre to help people learn maths. I will just give myself a little bit of a disclaimer. If you want to come and you want to ask about some very fancy differential equation solving method we may not know, we're very good at what's in first year and what's in high school in an ordinary degree. But if you're expected to know things that are in third year of an ordinary degree, might be a bit harder for us. But we're very good at interpreting lecture notes and interpreting textbooks. So if you have a textbook, we can help you understand what's there. Okay? And also, we're not involved in any of your assignments. So if you do come and say, can you help me with question 3, it may be useful to bring the assignment so that we know what question 3 is. We won't do it for you, but we will help you figure out what to do. That's how the Maths Learning Centre works. I'm sure as you go along, you'll see me a few more times. I tend to come to lectures. Next week, I'll be talking about statistics twice. The first one will be about statistics used in research, and the second one will be about assumed knowledge for a statistics course like statistics in engineering or intermediate econometrics 2, which are there's one like research methods in education. There's lots of them. So anything with research methods in the title has usually got statistics in it. Thank you very much. Enjoy your afternoon, and I will see you next week.